Hello everybody, this is Dr. Christopher White, and now let's move on to part 4 of Deformation part 2. Alright, so in the last few slides we're going to actually try and generally fit the types of deformation that we've been discussing into a more broader tectonic context. Alright, so here is our classic convergent boundary. And so obviously we know in the case of a convergent boundary we have two very large pieces of crust banging into each other. So I don't think it's too much of a shock that this is going to be an area in which we're going to suffer compressional tectonics. So obviously if we're going to suffer compressional tectonics, well, first of all, when it comes to the type of faults we're going to get, clearly it's going to be reverse faults and thrust faults. In terms of the types of deformation we're going to get, if we get ductile deformation, well, clearly we are going to get lots and lots of folding. Now, we are lucky in that when it comes to convergent plate boundaries, especially those associated with continent-ocean convergence, we obviously have a very thick piece of crust right here, which is made even thicker by the addition of a mountain range. And so what we have here is we have an area of continental crust that's going to get really nice and warm. And so that means a very large volume of this rock here is going to be very, very prone to ductile deformation. And so what we're going to see is, in the core of the mountain range, in the deeper portions of the crust, we're going to see extensive amounts of folding, because obviously we have a convergent, so we have a compressional setting and a ductile crust. Now in the upper portion here, as you can see, we are quite clearly going to have lots and lots of thrusting, or sorry, thrust folding. And you can see that's going to cause a lot of thrust duplexing. We're going to have layer, or have sequence, pushed over sequence, pushed over sequence. At the same time, additional mass is going to be added to our mountain range through intrusions in the crust. Of course, they will heat up high level crust. So they'll actually heat up the rock around them. And in some cases, that can also lead to folding at even higher levels in the crust. And we're going to have additional mass added in the form of volcanoes. So what we're going to have is we've got our mountain range, we have layers of rock being pushed one on top of another, we have intrusions, we have volcanics. And that's all going to help to combine together to produce a mountain range. So I don't think any of us are really going to be too surprised by what's going on. Now, in terms of the metamorphism that we've discussed, you can see it's telling us it's high pressure, low temperature, and high temperature, low pressure. Well, these are different types of metamorphism, and to be honest, we haven't gotten there yet, so we're not really going to worry about those. In terms of the deformation, well, obviously in the upper layers of the crust, we're going to see the brittle deformation. That's going to lead to the thrusting. And we see the same kind of features when we have a continent-continent collision. So in the case of a continent-continent collision, what do we see? Well, obviously, once again, we see extensive amounts of thrusting. What we'll also see is that in the lower portions of the mountain range, because remember, a mountain range is a very thick thing, and so that means in the lower portions of our mountain range, we are going to see increased temperatures, increased pressures, combined with a convergent tectonic setting, so once again the rocks are going to be squished, is going to lead to extensive folding. So these convergent boundaries are going to be very commonly associated with reverse and thrust faults and lots of folding. Now, in the case of divergent plate boundaries, of course, we have a situation where we have rocks being extended. Now, the thing that we've discussed about divergent plate boundaries is that obviously in order to make the magma that feeds a divergent plate boundary, we have to stretch the continental or oceanic crust. This leads to the crust above the divergent plate boundary becoming quite thin. So divergent plate boundaries aren't really going to be associated with much folding because, number one, there's no compressional force to really speak of, and number two, the crust is so thin that really the crust here is going to behave mostly in a brittle fashion. So we can see from these two diagrams that because the crust is under extension, it breaks into blocks, And obviously what's going to happen is we're going to form normal faults, and so these blocks are going to drop down relative to each other, and you can actually see it quite nicely in this diagram here. You can see this block here has dropped down relative to the seafloor here, and this block here has dropped down relative to this block, and so we end up with this stepped appearance. And so you can actually see the fault scarps essentially produced by each block of each normal fault dropping a block of rock down relative to another. So we're going to see that on the seafloor, and we're going to see the same thing over here in the rift valleys. And so what you're going to end up with is you're going to end up with a depression, because remember we've got blocks of rock dropping down relative to each other, so you're going to form a natural valley, and that valley is going to have a natural stepped appearance to it with lots and lots of fault scarps. So in this instance, normal faults, and that's going to be pretty much it. Now we might get some kind of ductile deformation associated with the magmas, and the rocks they heat up. However, once again, because this is a situation where we have only really tensional stresses going on, what's going to happen is we might see the rocks get stretched out in these areas that are being heated up by magma. Okay, so they may behave a bit like silly putty. However, they're only going to be a relatively minor component. They're not going to be that common. Okay, so in terms of metamorphism, it's going to be driven by heat coming off the intrusions. But once again, we haven't done those lectures yet, so we're not going to worry too much about it. So divergent plate boundary is primarily associated with normal faulting. Okay. Now, in terms of strike-slip faulting and shear zones, well, obviously we know that we're going to have a transform plate boundary. It's going to be associated with shear forces. We've got two pieces of rock moving past each other without any relative change in height. That defines a transform plate boundary perfectly. So when we try and shear our piece of rock, obviously, as this is the diagram we saw earlier, we're going to have one block moving past each other laterally with no change in height. So where do we see these kind of things happening? Well, of course, the classic example is the San Andreas Fault of California. And we also have the Queen Charlotte Fault, which goes along the west coast of Canada. So it goes pretty much all the way from just about north of Vancouver. No, sorry, I do apologize. Yeah, just about north of Vancouver, all the way up to the Alaskan-Canadian border. And that's another strike-slip fault. It's just like the San Andreas Fault. And one day, when tectonic conditions are correct, they will actually join up to form one continuous long transform fault. So the other place that we see substantial quantities of transform faults is, of course, associated with spreading ridges on the seafloor. And now you might have to remember back just a bit to remember this, but if you remember, spreading ridges on the seafloor, they have a very distinct stepped appearance to them. And that's because portions of the spreading ridge will move at different rates. So some portions of the spreading ridge will spread very, very quickly, and other portions of a spreading ridge will spread more slowly. And so this means that because the different portions are moving fast and slow, it means they'll actually move apart from each other. So some parts, because they're spreading really, really quickly, will accelerate away from the ridge, and some parts, because they're forming crusts more slowly, will stay relatively close to where the ridge started. And so it leads to this stepped pattern. Now, the only way to allow this movement, of course, is to have transform faults either side. And because you have these transform faults either side, it allows pieces of the spreading ridge to move depending on how quickly or slowly they are producing new crust. So this is the other location where we'll see substantial quantities of transform faults. So just to give you some idea, so this is a LiDAR image. Now if you look very, very carefully around California, you'll actually see quite a lot of this. So this is a LiDAR image around the San Andreas Fault. So the thing you'll notice is that if we look at this river here, look how it comes down, and it comes down pretty much straight. However, if we look at this channel here, we can see it comes down, then all of a sudden, bang, right angle, then it continues. Same with this dry channel here, comes down, bang, down it goes again. So we have two right angle turns here, don't we, for both of these rivers. That's because this piece of rock here, one block, is moving obviously to the left, whilst this block here is remaining still. Okay, so what we're seeing here is we're seeing this block drifting this way. So this channel here used to be there. However, because this block has moved to the left, it's taken this channel and it's transported it sideways. And the river has simply followed along with it. And so you can see that explains why it comes down. We have a right angle turn here, right angle turn here, and then off we go again. So this is another indication of transform fault movement. So let's go through this again. Convergent plate boundaries. Compressional tectonics produces reverse faults, thrust faults, and folding. Divergent plate boundaries produce tensional tectonics, so extension. That will produce lots of normal faulting, and also lots of things like fault scarps and rift valleys. And finally, we have shear transform plate boundaries. Obviously, they produce lots and lots of shear faults, strike slip faults, and that's about it. So okay, so those are your three types of plate boundary, and those are the main types of deformation associated with them. Okay guys, so that's it for deformation part 2. So keep an eye out for the lab videos, please. Alright, have a good day.